Shrikant, we have started recording in. Okay, so let's see.
Alright, so today I'm talking about mainly two different things. So the first one, which we started yesterday, about the strict convexity. Second one is Caffarelli's contraction theorem. These are the two things I'll be talking about. So let us remember, let us try to recall that our set of assumptions. So C, our C is quadratic form, so we are considering determinant, or maybe let me try to write in terms of optimal transport. CHY is our quadratic cost, and mu is FDS, mu is Y, and they are supported on a bounded subset, supported on a bounded subset X and Y, where X, Y are bounded and Y is convex. And on that set, F and G are bounded by constant, right? And the equation is, so under this assumption, equation is, so under this assumption there exists a convex function phi such that phi goes forward mu equals to phi. And the theorem we are trying to prove is the following: that this phi under all these assumptions, this phi is a strictly convex Alexander solution in X. Okay, strict convexity inside X. Here I forgot to mention X and Y are open bounded. So this is the theorem I proved last time. So the first part, we saw that phi actually solves the equation Alexander solution to H, right? So initially we saw that, so it solves the equation H, it is almost behaves like one constant inside X. So is that do you remember it? Can I write it more clearly? Right? So let me write very clearly. So you see inside X, so this is fx by g of gradient px, and f and g are comparable. So this is comparable to a constant. Okay, so let me write this way: lambda is equal to small lambda inside X. And also we saw last time that the Money-Ampere method outside X is 0, and which together is that he solves the Money-Ampere equation Rh when when H is something like H is supported on X and bounded below bounded states away from 0 and infinity inside X. The outside is 0, right? And here I'm sorry, I'm using phi, but I think yesterday's notation was phi hat, right? First we extended it, and then so this is the equation satisfied. Okay. All right. So the first theorem is so we already proved that it's the Alexander solution inside X, and now our task is to show the strict convexity of X. Okay. So let me. So what do I mean by strict convexity?
No, X is also convex.
No, X is not convex. See, so last time I mentioned, so here in this, you can define a convex function on a general domain omega by saying that it has a convex extension over Rn. Okay, so maybe so basically there exists a U bar from Rn to R union / infinity, which is convex. when you restrict your U bar to omega, this is H. So this is the notion of convexity. All right. So what do I mean by strict convexity? Right. So the definition is that in general, if you consider 2 points, and convexity, this is less or equal to t times f of x1 plus 1 minus t times f of x2. Okay, so this is from the convexity, and strict convexity is that equality holds if and only if x1 equals to x2 or one of them t1 t equals to 0. Okay, so otherwise, if this doesn't happen, then strict convexity. Pictorially, what is happening? Let's suppose you have a two points x1 and x2. Okay, so and suppose if it's strictly convex, then so let me draw the line here. Okay. So suppose at some point, intermediate point, let us call it xt. Okay, if at intermediate point, when this strict inequality should go, right? Okay, so that is the point. Now, suppose your suppose strictly convex on this line, and suppose you are looking from here, right? So you from here, and you are looking in this direction. Okay, so U is strictly convex, right? So when you are looking from this direction, your value at this are same, right? So let me just draw it something like this. Values are same, right? So suppose at some intermediate point, it is equal. Okay? So it is strictly convex. So something like, so it is convex, right? And suppose at some point it is equal, right? So that means you see the convexity fails, right? So you cannot have this kind of situation. So at some point, if your equality holds, then it should be equal throughout the line, right? So is it okay? All right. So basically, if convexity fails, a strict convexity fails, then you have 2 points where the value is almost fi. Okay. All right. Okay. So these are the two. This is the thing I'm going to use. So suppose that the solution is not strictly convex. I think we have is not strictly convex. Then there exists a line, we call it sigma, where U is fi. Sorry, phi hat is fi. This is just a line. I mean, it could be unbounded or bounded. Okay, so I have 4 cases. Okay? So this line is I have 4 cases. So let me do it one by one. So suppose sigma is a whole line. Okay, so you are in Rn, and this is just the whole line, right? And on this line, U is fi. All right. So the case one is sigma is a whole line. And on this side, U is fi, right? So just you can assume that you just takes the value for the line. I mean the same value of the line after subtracting the hyperplane. Okay. So in that case, see U is convex, right? So U is convex. So let us say something like this, and on this line, U is fi. Okay. So let us take any other point, and let us take some differential at this point, a tangent. So you have this line. The graph of U must lie above the tangent line. Right? So here your value is U, and you have a hyperplane which is supported at some other point. So this line should lie always above this hyperplane, right? And when is that possible? It's an infinite line, right? So if it is slightly tilted, I mean, this is possible only when they are orthogonal, right? Otherwise, it is not possible. So technically, all these hyperplane should lie on the orthogonal complement of this line, right? So basically, in that case, the subdifferential we have of RA lies in a let me write in RN minus 1. So pictorially it is clear, right? Okay. So in that case, the Monge-Hempel method is considered. Take the Monge-Hempel method, then it is vanishes. But our equation is that the Monge-Hempel method does not vanish inside X, right? It stays away from 0 inside X. So this equation is quite, it's not possible. The second case is that is 2. So if it is not an infinite line, so then it must have a exposed point. Okay, so I think we haven't said anything about exposed point, right? So let me just recall what we mean by an exposed point. Okay, so you know that if omega is a, I mean, if you have a convex compact domain, then it is the extreme points. If you consider all extreme points of this domain omega, and if you take the convex R, so that then this is precisely your form omega. When omega is convex and compact. And the extreme points are those points which cannot be written as convex combination of 2 points. For example, here, right? So this point can, or let us consider a 4. These points cannot be written as a convex combination of 2 points. From the pictorial, it seems like the supporting hyperplane should touch at only one point, right? But it is not always the case. As this example says, so suppose your domain is something like this. So let us call it 0. Okay, and suppose it is going up like a rate of say mod x power alpha, x power alpha, that alpha is bigger than that. Okay, so bigger than. Now let us look at this point. Okay. All right. Okay, so of course this is a extreme point, right? Not a strong. This is an extreme point. But if you consider a supporting hyperplane around this point, then you see because it decays faster than the linear, so this is the only supporting hyperplane, right? So the supporting hyperplane also contains a lot other elements, a lot of other points other than this 0 point. Okay? So this is the distinction between extreme point and exposed point. And exposed point is the supporting hyperplane. Okay, so exposed point say it's not in omega is if the supporting hyperplane a intersection say x naught intersection omega is only single. Okay, so that is the definition. Okay, and from this picture you see all the exposed points are extreme points, but not the converse is not. Alright. So of course, I mean, if you have if you have a supporting hyperplane which contains only that point, of course this point cannot be and I mean it has to be an extreme point, right? It cannot be any other. You don't have any other option. Okay, so regarding this, you have another theorem in convergence which says that the exposed points are the extreme points are limits of exposed points. Or in other words, I mean, you can approximate. Sorry, you can approximate extreme points by exposed points. Okay, so basically, if we are in a compact situation, and if we rule out all the possibilities that it doesn't have a exposed point, then it doesn't have an extreme point, and therefore that cannot be the case, right? So all we have to exclude is that this line doesn't have an exposed point. So case 2. So if this is not the line, it has to be a finite line, and therefore this implies that sigma has an exposed point. Okay, so now under this we have 3 cases. So case 1 is exposed point, where does this lie? Case 2 is that this exposed point lies somewhere outside X bar. Okay, so where you remember that Mon-Ampere is at times. Okay, so let me draw the picture. Okay, so this is my sigma. So yeah, so this is my sigma. Okay, and this is the point X bar, and it is lies somewhere outside X bar. Okay, so this is the boundary of my X bar, and this is my exposed point. So the graph looks like something like this. Okay, and so I'm drawing this picture something like this because I'm subtracting the hyperplane, right? I already mentioned that in such a case the value should be affine. So if I subtract this hyperplane, you are in this situation, okay? Where you can always, with continuity, you assume that this hyperplane is basically parallel. I mean, it has parallel to x1, x. When hyperplane is 0, L equals to 0. Okay, so in this situation, okay, so Agni mentioned one of the important points about Mon-Ampere equation is the affine invariance. So, okay, and also he mentioned, I think, a few clusters or the John Lewis lemma. Okay, I'll come to that, but from this picture. Okay, so just we don't have to go there right now. Just let us look at this picture, and suppose you let us consider a hyperplane something like this. Okay, it doesn't touch x. Okay, and let us look at only this portion of the. Okay, so we have something like this. Only something and something like this, and where the Mon-Ampere method vanishes. Okay, so in one dimension, what is that means? Forget about for the moment. Let us look at about one dimension. So one dimension Mon-Ampere method is 0, meaning p double prime 0, right? So that means p is affine. But does this function looks like affine to you? It definitely not affine. Okay, so this kind of situation cannot happen. If in high dimension, of course, if high dimension, the determinant vanishes. That means at least one of the eigenvalue vanishes. That means at least one direction it is affine. Okay? So at least one direction is affine. But let us look at this. Let me tilt the picture so that this portion becomes 0. Okay? So this is, you have other direction also, but at least in one direction it is affine. Let us look it. Let us look from the top. So you are looking from the top in a picture, something like this. Okay? So this is your domain, and suppose this is where it is affine. All right. So this is why it's affine, but the boundary values are 0, right? So on this whole line, it has to be 0. But inside this is convex, right? So if you take any point, okay, and you see it is always less or equals to 0. So if you consider any point, if here it is strictly less than 0, strictly less than 0, or less or equals to 0, then by convexity it has to be strictly less than 0. So that cannot happen. So in any other direction also it has to happen. So this also excludes the situation that a x part cannot lie outside x part. Okay. So the third situation is case 3. The third situation, x part lies interior in the interior of the domain. Okay, so this is the hard part that I mean one of that the Caffarelli's alternative will exclude the result. Okay, so here is a picture. Okay, so this is x. So this is your whole x, okay? And x part is an extreme point. Okay, so this is your x bar, and it is the graph is perfect. The graph is something like this. Okay, so let us make some assumptions. Assume, okay, as I mentioned, your supporting hyperplane is 0. Okay, and the sigma. So sigma is the line where it is affine. So let us say 0 is inside sigma, which I can always assume 0, and so this is in the z1 direction, right? So sigma intersection 1 bigger equals to 0. This this is contained inside X. So, this portion is X, and let us assume that X bar is equals to A bar times in the direction of E1. Right? Sorry, A times direction of E1. So this is your A. Okay, so basically this is your sigma, and this is the extreme point. Okay? Again, I mean, here the important point is that X bar lies inside X. Okay, so here the Monyan parameter inside X bar, the Monyan parameter does not vanish, right? So let us consider this hyperplane, which passes through 0 and this one. This hyperplane is precisely epsilon times 2. Okay? Now let us look at all here. Okay? So remember that Monyan parameter does not only doesn't vanish, it has the upper and lower bound. Okay? So if your convex function, so let us look at only this bit, okay? And let us call this domain is epsilon. Is epsilon. Now, Amit mentioned about sorry. You will do it.
I will for regularity.
For regularity, you will do it. Okay. So I'll just okay. So basically, the main idea is that you see, if you have a convex function, okay, and suppose that the domain contains a significant amount of balls. Okay. Now, if so, suppose your this is B1. Then now let us consider the point where it is minimum. Okay. Now let us look at the cone. Here. Let's look at the cone, and this is your QX. What QX. Okay. And right. So you see this cone. Yeah. Maybe I will do it different. So the point is that see, your Monyan parameter does not I mean stays bounded away from lambda, right? Lambda. That means stays bounded away from lambda. So the minimum point. So if it vanishes on this line, so you have a module of convexity, right, from bounded above. So the minimum cannot be too small. Right? So it has to be like a little bit. I mean, this bound should reflect on how. So here I'm saying that this is normalized. There is, you have a fall, and it is also the omega is contained in n and p1. So basically, I mean, you don't have a. I mean, the infimum should not be too small. It should depend on p1 and which basically what Agni also mentioned about the maximum principle. So if you have a curve around, so if two functions, convex functions, if this is lies above this one, then if you consider any hyperplane and you flip it slightly sufficiently down, then it will also be a supporting hyperplane, and therefore the Monyan parameter should be bigger equals to the Monyan parameter of this one, right? And so if such a thing happens, then u should always, sorry, if u is bigger equals to v and the Monge-Ampere meter of u is greater equals to the Monge-Ampere meter of v, then this implies u should lie always above v, right? So this is this is fine. This is fine. Right? If it is like below, right, yeah, this is fine. So you should always, so if you have a V1, then you can basically found a cone or a maybe ball, yeah, a parabola. Right? So since you have a lower bound, you can basically form a barrier which will give you some lower bound on the minimum. Right? So here in this case, what happens is that, so you see this point x bar. Okay, so let us tell this. Let us look at this. This is the point x bar. This maybe the picture is not something. Suppose this is the point x bar, and so understanding the picture slide. Okay, so this x bar is almost close to the minimum point, right? And the minimum point is almost close to the boundary of this point. Okay, so basically the idea is that the minimum point is basically going to zero in a slower rate than it is going to the boundary. Okay, so you see here, suppose you have a convex function which is which, let me draw the picture here clearly. So it vanishes on the boundary of the domain point. Okay? So let us consider a point here, ux, x ux, okay? And this height is basically ux. So this distance is basically distance from x to the boundary, and this distance is almost, I mean, comparable to say diameter of omega. Okay? Radius of whatever it is. So see, suppose this is very small. Okay? The value of u, see here, then let us draw the cone. Now, what is the subdifferential of this set? Okay? So the subdifferential is precisely, so here you have this line, you draw the perpendicular is 90 degree, and here you draw the perpendicular, this is 90 degree. Okay, so you see, the steeper it is, the flatter it is. The flatter it is, I mean, it is much steeper. Okay? Now, if you intersect at the -1 level, so these are all the subdifferential. So basically, the subdifferential, see, depends only on this angle and this angle, right? And this angle depends on the height ux by how much distance from the boundary, and this angle also depends on the height by how much this angle depends on the boundary. And you can quantify those things by Alexander's principle and the maximum principle. You can estimate the value of ux by a dimensional constant times diameter of omega, okay, times the distance x to the boundary of omega, and the Monge-Ampere meter of Monge-Ampere meter of u. Of course, here it will be some power. Okay, so this is basically tells you that at how much rate it is going to zero. Okay, so here in my case, the Monge-Ampere meters are bounded. Okay, so let me just forget about it. The Monge-Ampere meters are bounded, and about the normalization you talk about, so it is always contained in the ball, right? So that ball of radius n, so the diameter is also bounded. Okay, so basically this is some dimensional constant or some constant which depends on its parameters like the distance of it, right? So so this tells you that, I mean, you the point of minimum should lie at some distance if your Monge-Ampere meter is stays bounded away from 0. Okay, all right. So the idea is that here, see, if epsilon is the minimum point, so let us look at this picture. So suppose this is the point where minimum is active. Okay, now this line and this line, not. Let me draw. That's point phi 0. This is phi 1, and this is 2. Okay. Now, see the distance between these two. Okay, so I just lift the plane slightly up. So this distance, this is A, and therefore this quantity, this is an exposed point, right? So if epsilon is sufficiently small, then it will go to 0, right? So so this plane should go to this plane, right? So every point should lie above this plane. So as epsilon go to 0, this distance would always go to 0, and let me write as a bar plus small o of mass. Okay? So when you normalize it, the picture will look like the picture looks like this. Okay, so and this is the point epsilon, which is the point of minimum, and this is these are the normalized. By normalized, I mean that it is just a affine transformation. Okay, and up to the scaling which mentioned, which is determinant power 2 by k. Okay, so now the affine transform that preserves the ratio of the distances. All right, so you look at this place. So this is a bar, and so this ratio. So this distance is small o of 1, right? And therefore the distance between this plane go to 0. Okay. So the ratio, so phi 1 distance between phi 1 and phi 2, and distance between phi 0 and phi 2. So this is at least a, and this goes to 0. So this goes to 0. And when you normalize, it will preserve the ratio. So after normalization, it will preserve the ratio. So this will also go to 0. Now pi 0 and pi 2. Now after normalization, it contains a ball V1. So the distance, so this is your pi 0 and this is your pi 2. So it contains the ball V1. So at least the distance is 2. And therefore, the ratio between this go to 0. Right? So the ratio between these two go to 0. So the distance between this go to 0, and in particular, the distance from x epsilon to the boundary go to 0. Okay? Epsilon to the boundary of x star go to 0. So here I have defined many things start. So by star I'm
So I will do it in details in my, because he's talking about normalized, but he's not.
Yeah, I haven't
too much of
defined the
detail.
normalized,
It is
but,
not a sub detail. So there is a lot of
Yeah.
ingredients underlying. The key idea is that the point of minimum cannot be too close to the boundary, but this x bar after you lift this plane is almost like the minimum, comparable to the minimum.
Yeah.
So you cannot inscribe a ball, because if you do, as you let epsilon go to 0, x bar goes to the boundary,
Exactly.
and that cannot happen. So this has to be done in a lot more detail. So
Yeah. So this normalization will take some time. So the whole idea is here that this point x bar is close to the minimum, but at the same time it is also close to the boundary. But the rate at which, of course, you see this will minimum will go to 0, but the rate at which go to 0 is far more quicker than at the rate with this distance go to 0, which is not possible from this Iceland recognition. Okay, so this is why this excludes the case that it doesn't contain the extreme point is not inside the boundary. And the final case is 4. quote is the X part lies on the boundary of X. Okay. Now here is the main problem. So again, so the idea is, you see, here we lifted this plane slightly up, and we could capture the Monge-Ampere method. But here the problem is, since this is on the boundary of X, it cannot capture. I mean, it doesn't have the Monge-Ampere method. You see here the picture what we did here. If we have a lower bound, then probably the minima cannot be too close to the boundary, right? Because see, if it is too close to the boundary, you have to go a little bit quicker, and that will contradict. So it is the Monge-Ampere method has to go close to zero. So this kind of picture is not admissible if you have a lower bound on the Monge-Ampere method. But now it is on the boundary, and our Monge-Ampere method vanishes at the right hand side of this boundary, where we proved last time. So this kind of picture is really admissible, right? So here the idea is that here we lifted the plane slightly up. So you have to lift the plane sufficiently up, okay, so that it will capture the Monge-Ampere method from the inside. Okay? So here is the idea. So let us take R naught, the diameter of omega, and without loss of generality, we assume that X bar is zero after shifting. Okay? After shifting, and sigma. So again, it is on the boundary of X, and sigma is the plane where C1 lesser equals to 0. Okay? So here the picture right now is something like this is 0, and so these portions are inside here, and here something like minus 2r not. So this whole portion contains the X. Now what you are going to do, you are going to just lift the plane, phi hat epsilon X is equals to phi hat of X. Earlier we subtracted epsilon times C1, right? But now we have to lift the plane sufficiently up, so 2r. So here basically we have lifted this plane sufficiently up to capture the Monge-Ampere method. Now,
just to understand it correctly, this beautiful idea. So you are trying to tilt this plane up so that you are able to generate a lot of large sections below after normalization. And that cannot happen because you have an upper bound on the Monge-Ampere measure also. That also has to come to play.
Upper bound
and the upper bound on the Monge-Ampere measure will tell you that the sections are bounded from above.
So basically, so this will tell you actually the Monge-Ampere method. No, here is also, I mean, see, no.
I'm just trying to understand this.
And this will capture sufficiently Monge-Ampere method.
Exactly, right? Which is on the degenerate path.
The minimum cannot be too small. But the planes, I mean, the same idea. The planes are actually going to 0. It is also 0, so and that will contradict the.
So I think at the picture, at the normalized picture, it will just tell me that along some directions,
Yeah,
the height compared to the height of the section, it will be height times a function of h which goes to infinity, and along this other sections where it's flat,
right,
it is at least a size 1.
Right.
And the bound on the Monge-Ampere measure from above will tell you the volume of the sections cannot go more than h to the n by 2.
Right.
And that will sort of lead to a violation. So I think so. This is kind of like cleverly tilting this tangent plane near the boundary.
Yeah.
I mean, it's not boundary, but going a little bit inside in a way so that you are able to generate last sections.
Yeah.
And this I think is
right. So let me draw the pictures.
So this is the main case of this proof. The third case is I think is there in Monge-Ampere one.
Yeah.
The eighth code is I think the beautiful line.
Right.
Debabrata is just writing.
Yeah. So this is your 0, and you lift it then sufficiently up. So this is 0, and which is our extreme point x bar. Okay, and so let us look at this portion of the boundary. Okay, now sigma. So let us consider a point let us call it x naught, okay, which is inside x, and therefore you have sufficient distance, and so that the ball is contained inside the domain omega. Okay. Now, if you normalize after this normalization, okay, so L, suppose L epsilon is the Jones map which normalizes your section. So this is your whole section. Okay. Is epsilon of epsilon. So this will contain the ball V1, and therefore L epsilon inverse V1 is contained inside L epsilon, and this is again bounded by the diameter, say call it R1. Now, so this implies L inverse has normal L inverse is V1. V1 is less or equals to R1, right? And therefore L epsilon of x minus L epsilon of x bar is bigger equals to 1 over R1 times of x minus x bar. Okay? So after this normalization, this tells you that this ball V delta R, V delta x naught. So this contains inside x, and this is at least delta distance away from the extreme point. So after normalization, this will be at least delta over R1 distance away from the normalization. Okay, so after this normalization, let me look. So this is my normalization. Okay, so this is the point x bar, the extreme point. Okay, so this x naught maps to some place x naught. Okay, and this has sufficient distance, which is delta over R1. Now that will capture the Monge-Ampere method, right? So this tells you that, see, this is the normalization. Okay, so now you are looking from down. Okay, so let me you are looking from down, and so this is x bar, L epsilon. It may be somewhere very close to the boundary. All right. Now V1 is normalized. V1 is somewhere. Yeah, let me draw x bar later. So suppose this is the ball V1. Okay. So at least this is convex. So it will contain the whole cone, right? So x bar, wherever x bar it is, and suppose here is x bar, somewhere here is x bar. So this distance is at least delta over R1, right? And therefore, if you consider a section which is like distance from delta to the R1, so this will not intersect the extreme point. And here you have a non-trivial method, right? So basically, this all translates into something like the Monge-Ampere method of the normalized would be some constant which depends on R1 or n, right? So see, this cone has a sufficiently Monge-Ampere method, and that tells you that the subdifferential cannot be too small. Right? This implies that B is 0 delta over R1 up to a constant here. Okay, so let me call it C1 cannot be whole content inside the subdifferential of P hat, right? And therefore, maximum of the subdifferential should be at least bigger equals to up to a constant times delta over R1. Okay, and here we are looking at a distance which are basically 2 over R distance out, right? And P is in the subdifferential P hat of x, and this is inside the region where, let me call it epsilon delta, which is basically 2 epsilon distance away, distance from x to the boundary of this epsilon star is at least delta over 2R1. All right. So once you have this tells you that you cannot be too small. Okay. Cannot be minimum of u cannot be too small. Follows from the Lipschitz form of not exactly Lipschitz form, the subdifferential form of c f of c is bigger equals to f of x plus 3 times z minus x. Okay, so let me take it to the this side. This is minus. This is bigger equals to if you so yeah, and this distance. Okay, so this is bigger equals to 2 times norm L infinity, right? And here, if you consider so if you consider any direction, right? So this is bigger equals to mod p times basically distance from if you vary. So here is your x, okay? And this is the distance. Okay. Now this is distance from to the boundary. Now within this region, you can vary in every direction. So this will at least be distance from x to the boundary of x. So basically, if your p is if your p is not small and the distance is sufficiently far, then the minimum is cannot be too small, right? And therefore, the minimum is epsilon delta star. This is where your two distance delta one r1 distance away, phi at epsilon, and after subtracting this one, normalized cannot be too small. Cannot be too small. But again, because this is an extreme point, the same principle tells you that the direction, the distance between this plane go to 0, right? Which in turn will give you the distance between this plane will go to 0. And again, from the same thing that see here at this point where the minimum it cannot be the point is far sorry. So the distance is again, because it's an extreme point, the distance goes to 0, and since point length preserve the distance, it will go to 0, right? And this point is actually the minimum point is almost comparable to the point, the value at x naught, right? Which is sufficiently this is. So of course, I mean this is not very clear to figure out from this what I just mentioned, but I hope that.
I think in a way the key new idea compared to his earlier works on one was this boundary.
Yeah.
That you tilt this plane in this manner.
Right.
Because the other cases, the third case is kind of the interior, which is
Right.
out by the
around 90.
Incredible how he even came up with this idea.
Yeah, so that you can capture at least significant amount of portion from the interior.
Which is in some sense, I mean, just a little comment. It is in some sense similar to when it shows that the subspace where the function fails to be strictly convex has dimension less than n by 2. This kind of again is based on a sort of a tilting of this argument where you end up capturing a section which has good mass. But again in a more sort of a expanded way that goes to infinity and which cannot. But I think in this case, I mean, you just need a lower bound to know that.
I think I have taken a lot more time. So the last part I'm going to talk about is contraction theorem, or sometimes you probably also be heard about actually log-concave perturbation. Here is the setup. Again, our cost is quadratic, and we are in Rn, and now my measure is Gaussian, and mu is a log-concave perturbation of the Gaussian in the sense that e power so minus some w minus x square by 2 dx, and here w is convex. All right. So this is my setup, and phi is the Brenier map. Phi the Brenier map, which pushes forward to nu. Okay. So under this assumption, Caffarelli showed that Brenier map is on. Sorry, Brenier phi is a Brenier map. So Brenier phi is contraction. That is minus Brenier phi of y is less or equals to minus 1. Okay. So that is incredible. I mean, and here, we'll probably talk about that second derivative of the solution, PW, that is a sub-solution of the theoretic equation. Right? So this is the key idea that when you prove this theorem, this is something different with all things. Okay, but the proof is quite nice and simple, and after I understood the proof, I mean, it was feels like simple, but let me explain what I have understood. Okay, so all right, so this is the main theorem. This is very easy to understand in dimension 1. Okay, so let me just do it in dimension 1 first. So suppose if you have e power minus x square by 2, and suppose and nu is, so the Monge-Ampere equation becomes in dimension 1, okay, double prime, which is the determinant f square over 2, and then g of gradient b, so is e power minus w e prime minus e prime squared by 2. So this is the Monge-Ampere equation. So remember, the right hand side is basically fx by g of gradient cx. Okay. Now let us take a log e double prime, and then you have minus x square by 2 and plus w, sorry, p prime and plus p prime squared over 2, right? So this is correct. Okay. So now let us differentiate it 2 times. Okay. So if I differentiate it 2 times, the first time I will get p double prime by phi triple prime. Okay. So if I differentiate it again, then this is square and this is 4 times derivative, second time derivative minus double prime square. So this is the left hand side. The right hand side, if I differentiate twice, this is minus 1, and this is plus. If I differentiate once, then this is w prime p prime times p double prime. I have to differentiate it again, then w double prime p prime square, and what is the other term? So w double prime, w prime p prime times p triple prime. Okay. Now this one is, if I differentiate once, then it is p prime p double prime, and if I differentiate it again, then when I differentiate this one, p prime p triple prime. All right. Okay. Now this one, let me make it square. Okay. See now, suppose x naught is a point of maximum. Okay. Point of maximum of p double prime. Okay. And assume that it is an interior point. And let us compute at the interior the derivative. Okay. So this is a point of maxima. So the yeah.
So yeah. Next one. Minus there only.
Yeah. This is triple prime.
The double prime in that minus.
This one. Okay. Thank you. Okay. I mean, it will not matter. Okay. So at maximum point, the fourth order derivative should be less or equals to 0, right? And this is already has a sign. Okay, that you will see also in the higher dimension. Okay. So this has a sign at the point of maximum. This is less or equals to 0, and this quantity has a sign. Okay. Now here, see, at the maximum point, P double prime vanishes, triple prime vanishes. P triple prime vanishes. W is convex, and this is a positive, right? So W is convex, so W double prime is always bigger or equals to 0. So all you get, this quantity, left hand side is less or equals to 0. So you get that 0 is bigger or equals to -1 plus P double prime square at the point of maximum. Okay? And that gives you that P double prime is less or equals to 1, and this is already convex. And therefore phi is phi. Yeah.
My feeling is that one is that you get that all the solutions are classical by what you just said.
Yeah.
And the second thing is that in higher dimension, I'm quite sure that Caffarelli was very much inspired by Pogolarov's computation of the estimate of the second derivative.
Okay.
And now this W double prime just as the right sort of. Wonderful.
And
so it's similar, no? That very differentiates is twice and puts several information together. UKJ, capital JJ, U.
Right, but except that, I mean, you see, you cannot differentiate this equation. Of course, you have to take the difference quotient, and that I will explain in a moment. Okay. So.
Why can't you differentiate the equation?
No, I mean, so you have only C2, right?
No. From C2 you get all the way up to C infinity.
But if W is only, I mean, you don't have any regularity on the W, right?
Oh, I see. Oh, so assuming that W is smooth.
If W is smooth, then you can do all.
Then the regularity theory applies by what you did.
Yeah.
But even then, it's interesting.
Of course, I mean, yeah. But yeah.
I think the regularity of W, is it really a very serious thing, or I think the interest is also in the smooth convex W. But then also it's a very interesting kind of.
Right. I mean, see, the computation what we did for P double prime, I have to do it for difference quotient, and the computations are.
No, it is the same because the thing is that because the log of determinant is a concave operator, so the extreme, so the incremental second order difference quotient still has a sign.
Right. So that is the main idea. Log of the determinant is convex. Right? Okay, so
interesting. Interesting. So I think this one dimension is the key punchline, the key idea. This calculation is the main.
Right, and I mean another key thing is that see here I'm assuming that the maximum is attained at the interior. Okay. But I have to show that this is indeed the case, right? That and for that, what I'm going to do is assume that the support of W is say E0R. So, which is, I mean, by approximation you can always do, right? Because by approximation you take a sequence of support increasing, and then you still get the result. If you get the result, then yesterday I mentioned about the stability of maps, which converges in measure. And hence, up to a subsequent, it will converge pointwise almost everywhere, and therefore the same estimate is present. And here, since we are in a good setup, you see W is convex. Okay, therefore this is at least least stitch. Okay, so basically you get the solutions are C to alpha low, and therefore all the median map these are all, I mean, continuous. Okay, so continuous. So all these maps are continuous, and therefore this holds everywhere. So I have to prove that maximum is attained. Yeah, at the interior point.
But is it not okay if now that you have from a previous result in all dimensions is strictly convex?
Yeah.
And it's a subsolution.
Yeah.
But there has to be an interior maximum for the pure second derivatives or in all dimensions. Because finally, for high dimensions, you want to show that along any pure second derivative, UEE is less than equal to 1.
Along any derivative, UEE is
less than equal to 1.
Yeah, exactly. Yeah.
But that is now okay, or maybe some work is needed. Because now if it's strictly convex,
right,
and UE is subsolution.
Yeah.
So therefore, it's kind of so the maximum of UE happens at.
Right. I mean, that is mainly the idea, but I mean, you have to be, and that is the heuristics, right? I mean, you have to be precise. What do you mean?
Right. Okay.
So, I mean, basically, the idea is that suppose this is your support of the measure, right? Now, let us take a point say x bar, say x naught, or say x1. Okay? And suppose this is the image dx1. Okay? So this is the image dx1. Now let us look at only this part. Okay? So basically, what saying that the optimal map, okay, when you let x goes to 0, they will basically concentrate around this point. Okay, so this is another thing that we have to be, taken care of seriously. Okay? All right, so you see, this is where you need, stability, and that it is also bounded from below. I mean, see, from our assumption, so this is bounded from below, right? And so let us look at this portion of the boundary. Okay? So if at a point, so let me call this gamma. Okay? So let us take a point Tx in gamma. So this is the point Tx. Now, in one dimension, optimal maps are monochrome, right? So this Tx, this x must come from some place right to x1, right? And if I denote this domain omega, then this T inverse omega, so x must belong to omega. So basically, T inverse of gamma, that is the optimal map, which must contain inside omega, right? And therefore, if you take the measure, so this goes to 0, right? And this is mu of gamma. Okay, so nu of this interval, so that will go to 0, and that will that tells you, and this implies the Levens measure. Okay, so since nu the density of nu is bounded from below, it tells you the ln of this measure of gamma, which is r minus. This will go to 0 and x goes to infinity, and therefore Tx will, in 1, and which is precisely the modulus of r minus t, so that will go to 0. So this is the main idea, and in higher dimension, and of course, it means that you see, he will prove the C2 alpha regularity of optimal maps. See, here the supports are, the W is convex, and therefore the support is convex. So Brenier solution is the Alexander solution. This is the Lipschitz, and therefore at least it is C2 alpha low, and therefore this equation, whatever I note, A2C equals to e power minus mod x square by 2 by e power minus W gradient phi minus mod gradient phi square by 2. So this holds the classical sense. All right. So in high dimension, you have to just give some ideas, and we'll stop. Okay. So I just wanted to show how these computations hold. Okay. So in high dimension, what you consider is the second order. So x plus epsilon e, x plus epsilon e, x minus epsilon e minus 2 phi of. Okay, so let me call it epsilon. Okay, so this is basically the approximation of the second derivative of order epsilon. So almost into phi of times epsilon square. Right? Now we cannot differentiate the equation, so we have to do it. We have to do all the computations at this level. Okay. All right. Now my claim is that so this d epsilon x is actually go to 0 as mod x goes to infinity. Okay, I will again give a proof geometrically later. So for the moment, assume that, and therefore it has a maximum. Okay, so this also depends on E. This also depends on E. and P is varies over S in minus 1. And is equal to 0, so that this will go. So suppose, so it has the interior maximum, right? And we are taking maximum in both directions, x and e, right? So basically this is approximation of d2p et, right? And if I can show that this is less or equals to 1, then you are done. So if this has a point of maxima, then a gradient at that point vanishes. Okay, so suppose x0 is a point of maxima and e1 is the direction, then the gradient and e1 minus gradient 2 of x1 vanishes when you take the gradient with respect to x. Now you have another direction e, which is in the direction of s in minus 1. So if the take the gradient, it should be along the normal direction, right? And the normal direction is e itself. So gradient t is not plus epsilon e1 plus gradient t. Sorry, here I should this plus, and here it is part minus epsilon e1. So this should be in the normal direction, right? So let us take e1 ej, e1 to en, any orthonormal basis. This is the direction. So these two have the same component around any ej. So e1 ej is an orthonormal basis. These two have the same component in e2 to en direction. Okay? And all you have to do, you have to compute the e1 direction. Okay? All right. So all you have to do, you have to just compute the e1 direction. And again, if we this says that these two have the same component e to ej direction. And if you use the first equation, then you have the direction is basically phi j, right? So gradient phi x0 plus epsilon e1 dot ej is gradient phi at x0 not ej for j bigger than 1, and this is holds for both, right? And therefore if we compute the e1 direction, shall I just write the result and proceed? So if you compute the e1 direction, what you will see that gradient phi of x0 plus minus epsilon e1 is basically gradient phi x0 plus minus some delta times e1 direction. So this is what you will get just by doing this computation. So now here is the thing, and p epsilon has a second derivative, right? So the second derivative should be less or equals to 0. So determinant d2 phi d2 phi x0 plus epsilon e1 plus d2 phi x0 minus epsilon e1 minus 2 p x0, this is less or equals to 0, right? From the because it is maximum. Now here is again the log determinant. Yeah, so Omni mentioned that if you consider f of a is log determinant of a, then the derivative at epsilon equal to 0 f of a plus epsilon p is, we are taking the log, right? So onward determinant will cancel out. So this is trace of a inverse p, right? And you see in determinant, so this is the inner product, right? So this basically gives you the gradient. Okay? And Avnid already proved that it is log-concave. Determinant is log-concave. And therefore, f of b, the supporting hyperplane at A should lie above the graph, right? F of A times B minus A, right? So now here the inner product is this one. So this is the inner product. So the gradient is A inverse, and therefore gradient of FA is A inverse, and this is B minus A, right? And this is precisely trace of inner product is precisely trace of this one, right? Now if we apply this inequality for E2 3 x naught plus minus epsilon, okay, and add these two inequalities, then what you will get is that the log of the determinant is basically less or equals to 0. Log of determinant equal to 3 x naught plus epsilon E1 plus log of equal to 3 x naught plus minus epsilon E1 minus 2 times log of to 3 x naught less or equal to 0. Okay. And now you can use the equation. Okay, so this equation is satisfied classically. So this tells you that the first one is log of the determinant, right? So mod so I'm taking a bit too much time. Okay, so this is the first equation is half x naught plus epsilon E1 squared, then plus half x naught minus epsilon E1 squared, and from here minus 2 mod x naught squared, and I have log so minus, these are all minus, plus, and then corresponding to W, okay, so W of gradient phi x naught plus E1 plus W of gradient phi x naught minus E1 minus 2 W of gradient phi at x naught, and similar things for phi. Okay, I'm not writing, but see, now this quantity is less or equals to 0, right? Yeah. Now you see here W is convex, and we already have this one plus minus this one, so we can use the convexity to ensure that this term is non-negative, and this term is basically epsilon square. Okay, so if you compute it's epsilon square, and the remaining term here, what you will get is that if I you see the term here we get in terms of phi, right? So half gradient x naught plus epsilon E1 square and similar terms. Now these are all according to my computation plus delta E1, right? So if I do the similar computations, here we will get minus delta square, which is less or equals to 0. So basically what you get is that delta square is less or equals to epsilon square, and this implies modulus of delta is less or equals to epsilon. And what is delta? Delta is precisely if you compute from here, if you I mean, this is the difference between, you see, delta is precisely the difference between the gradients. Okay? Now you use the convexity, you will see what that. So delta basically gradient C x naught plus epsilon E1. Okay, if I consider E1 minus gradient G x naught by, I think is it okay? I'll just take and write it down. Okay, so I don't have time to calculate it.
I think key idea is really not about this difference question, because that is, I think, well known to people who do polynomial.
Yeah.
I think the heart of the matter is to assume W is kind of entirely smooth, because I think Luis Caffarelli was already used to using this incremental difference model in the context of fully nonlinear equation.
Right.
Because that is also needed as a passage from the viscosity theory to the full.
Right. So the key idea is the second derivative of the one number.
And now you have that the delta is like a strict separation that you have for the delta. If which is going to be a violation as you let epsilon go to zero.
Correct.
It comes from the strict convexity.
Right.
So there is
not strict convexity. You don't need strict convexity.
or at least the monotonicity of this.
No. You don't need it. You don't need the strict convexity. Of course, I mean it is needed for the smoothness of
But
the
the
system.
but yeah, maybe not for this.
Yeah, not really.
Yeah, because this is I think just the extreme of point.
This is just the extreme point.
This is just the extreme point.
Yeah. All right. So let me just write it down. What is my delta and this is basically this one half and then plus T1. Yeah. So this is my delta. Okay. Now, if you use the convexity, so shall okay. Yeah. So basically, what you have is that if you use the convexity, so you have the gradient h naught plus epsilon e1 minus gradient t of h naught. Okay. So this is basically your delta. So this is less or equals to epsilon. Okay. And now we use the convexity h naught plus minus epsilon e1 is bigger equals to c of x naught plus gradient p x naught plus minus epsilon e1 times plus minus epsilon e1. Okay. Yeah. So yeah, if you use the convexity, then you have this one and you add these two things up, and then if you take it to the other side, so 0 bigger equals to have this p epsilon, right, which I defined earlier, and this one is precisely like 2 epsilon square because you already have epsilon here, and some and this one is your delta, which is delta is bigger equals to epsilon. So you get and you have minus here. So this implies p epsilon is basically less or equals to 2 epsilon squared, which is bigger equals to 0. And this is the estimate you are using, right? And for so that it is equals to 0, the idea is almost the same. Optimal map, you see, when the optimal map is, okay, if you consider the limit 1 equals to infinity, so this actually concentrates on the diameter. Okay? So x by mod x times the diameter. Okay? So this is what and that will show that your phi is actually goes to 0. And here the idea is almost the same. If you consider a point x naught, suppose this is the point tx naught. Okay, you look at and this is 0. Okay, so this is the direction of x. This is the direction of x naught, and you look at a cone. Okay, look at a cone, and you look at this cone. Okay, so of course here you have this r somewhere. Okay, now the images of Tx should come from something like this one, okay? Because it cannot be if you have a point image here, then the angle has to be less or equals to pi by 2. So basically, it has to come from somewhere here. Okay? This is the zone, and this is the point x naught. And if your x naught is sufficiently far, and this portion would go to 0, which in turn implies that the area of this portion will go to 0. And when you, I mean, if the angle is sufficiently flat, then it says that if this is your x naught, then this portion goes to 0 as this is your 2x naught. So this portion goes to 0. Either of this portion go to 0, and which in turn gives you that the tx naught should convert in the direction of x. Okay, so I'm sorry that I took so many times. Yeah, this is the main idea. Okay, I'm sure that it's very hard to follow what I just told, but I have written a notes particularly designed for this symposium. So if you're interested, maybe I can share with you.
You can send it to me, okay, and then I have a group, symposium group.
Okay.
If you send it to me, I will scan and send to everyone.
Yeah.